welcome to the deep dive. So forget those dry textbooks today. We're kind of hacking our way to understanding tech better using a set of practice questions. These are for the H12-821 V1.0 exam.
Right.
Think of this as maybe your backstage pass. We want to demystify some core networking ideas, how data gets around, how we keep things secure.
Exactly. And our mission really is just to pull out the key insights about routing, traffic flow, security, stuff like that.
Yeah, without getting totally lost in the technical weeds.
Absolutely. And look, while we are using these exam questions, the real point is understanding the principles behind them. It's actually pretty fascinating how this stuff underpins, well, almost all our digital communication. So even if you're not prepping for this specific exam, these ideas, they give you a much clearer picture of how all this tech actually works.
Okay, good point. Let's dive straight in then. First up is a question about ISI levels. The answer they give is C. Level 1-2 routers can form adjacencies with both level 1 and level 2 routers. So what's the bigger picture here? Why have these different levels? Does it matter in like a real network?
Oh, absolutely. What's really interesting with IS is how it lets you build a much more organized and scalable network. Think about, say, a big university campus.
Okay.
You might have a local network just for the engineering department, maybe that's level 1, then another one over in humanities, also level 1, and then there's a main campus backbone network connecting everything that's level 2.
Right.
Now, a level 1-2 router, that's like your central admin building, It can talk directly to the local departments and it can talk to the main campus network.
Okay. So it bridges the gap.
Precisely. And this segmentation, it means routing updates within just one department don't flood the whole campus network. It keeps things much more efficient, easier to manage, especially when the network grows. Think about cloud environments too, where things scale up and down all the time. Very important there.
That analogy helps a lot. Keep things tidy locally, but stay connected broadly. Okay, next question. This one's about MPLS labels. The answer here is D. Labels are pushed, swapped, or popped during forwarding. For those of us maybe not wrestling with routers daily, why is this label dance so important? How does it help get my cat videos delivered faster?
Well, think of it like this. Imagine sending a package across the country. Traditional IP routing. That's like the package stopping at every single post office along the way.
Yeah.
And at each stop, they have to read the entire address, figure out the next step. Takes time. MPLS is different. It's like putting a special sticker, the label on the package when it first enters the MPLS network. Yeah, a label. And every router after that just looks at the sticker, doesn't need to read the whole address again. It just sees the sticker and knows exactly where to send it next. Pushing is adding the label at the start.
Yeah.
Swapping is changing the label as it goes through the network, maybe for the next hop. And popping is just taking the label off right before it leaves the MPLS zone.
So it is like a fast pass for network data.
Exactly. It speeds things up a lot. And, it enables more advanced stuff too, like traffic engineering, VPNs. It's more than just basic forwarding. It creates a much faster, more efficient path.
Makes sense. Okay, next one. How devices get an IP address in IPv6? The question points to answer B, SLA. SLAA. Sounds interesting. What's the magic? How does this self-configuration work?
Yeah, SLAC. Stateless address auto-configuration. It's actually a really elegant solution. Basically, it lets devices on an IPv6 network figure out their own IP addresses.
Without needing a central server, like DHCP.
Exactly. Not always, but often without needing a DHCP server, like in many IPv4 setups. Here's the gist. A router on the network sends out messages, like broadcasts, with the network prefix information.
The prefix, like the street name.
Sort of, yeah. A new device joins, listens for these messages, grabs that network prefix, and then it combines it with its own unique identifier. Think of it like its hardware fingerprint. It's a MAC address, usually. Right. And boom, it creates its own unique, globally reachable IPv6 address. So the network says, here's the street name, and your device says, okay, I'll use this unique house number. It simplifies network admin quite a bit in many scenarios.
That is smart. Distributes the work.
Right. And you mentioned DHCP. The key difference is DHCP is stateful. It keeps a list. It tracks who has what address. SLAC is stateless. The router just provides the basics. The device does the rest.
Got it. Okay, moving to keeping things smooth when the network's jammed up. QoS. The question highlights C, priority queuing, or PQ. How does this first-class lane for data actually work?
Right, PQ. Imagine a really busy security line at the airport. Priority queuing is like having that express lane for certain people, maybe folks with tight connections or, airline crew.
Okay.
In a network, different types of data traffic get different priority levels. So like a live video call, that can't handle delays well, so it gets high priority.
Makes sense.
But maybe a routine software update happening in the background, lower priority. So when the network gets congested, more data trying to get through than the path can handle right about, then the packets marked with higher priority. They get moved to the front of the line. They go first.
So my video call doesn't freeze.
Exactly. It helps ensure those time-sensitive applications keep working well, even if the network is under stress. It's amazing how just prioritizing certain data like that can make such a huge difference to, our online experience.
Definitely. You don't want pixelation because someone started a huge download. Okay, let's tackle BGP, Border Gateway Protocol. This is the big one, right? Routing between different internet providers.
That's the one, the glue of the internet, essentially.
Okay, the question here says option B, supports classful routing only, is not a characteristic. So what's the real story with BGP's routing?
Yeah, that's a really key point. BGP is a path vector protocol. It uses TCP for reliability. It supports policy-based routing. That means admins can set rules about traffic flow. But the idea that it only supports classful routing, that's wrong.
Okay.
BGP was designed specifically to support classless interdomain routing, CIDR.
CIDR, right.
Which is a much, much more efficient way to allocate and manage IP addresses online compared to the old ABC class system. BGP's ability to handle CIDR is, well, absolutely fundamental to how the internet scales today. It allows for flexible network sizes. So yeah, BGP is far more sophisticated than just handling those old, rigid, classful networks.
Got it. So BGP is built for the modern, flexible internet, not just old school classes. Okay, next is OSPF. Specifically, the designated router, the DR answer A says, it reduces the number of required adjacencies. Why is having fewer connections actually better here? Seems counterintuitive.
It does seem a bit weird at first, but think about it like this. Imagine a really crowded room, and everyone needs to tell everyone else some piece of news.
Chaos.
Total chaos, right?
Yeah.
If everyone tries to talk directly to everyone else, it's just noise, and nobody hears anything useful. The designated router, the DR, in OSPF on certain types of networks like Ethernet, it acts like a central coordinator in that room.
Okay.
Instead of every router needing to form a direct link, an adjacency with every single other router on that same network segment, they mostly just talk to the DR and maybe a backup DR, the BDR.
So they report to the coordinator.
Exactly. They send their updates to the DR, and then the DR distributes the information to everyone else. This drastically cuts down on the amount of routing chatter, the number of connections needed. It makes the network more stable, more efficient, especially on networks with many routers, like a typical office LAN. It's all about streamlining communication.
Makes perfect sense. One announcer instead of everyone shouting. Okay, next topic. MPLS VPNs and something called the route distinguisher, or RD, answer B says it's to distinguish overlapping IP addresses between different VPNs. Why? Why would different companies have the same internal addresses? And how does this RD thing stop things getting mixed up?
Yeah, it sounds strange, but it's actually super common. Lots of organizations use the same private IP address ranges internally, like 192.168.1.024. You see that everywhere.
Oh yeah, my home network uses that.
Right. So imagine two different companies both using that same range internally. Now, if they both connect to the same service provider using an MPLS VPN, well, how does the provider keep their traffic separate? If it just looked at 192.168.1.5, it wouldn't know which company it belonged to.
Ah, I see the problem.
The route distinguisher solves this. It's like a unique tag or prefix that the service provider adds to the customer's internal IP addresses within the MPLS network. So company A's 192.192.1.5 becomes, say, RD8.192.168.1.5, and company B's becomes RDB.192.168.1.5.
So it makes them unique.
Exactly. Unique within the provider's network, even though the original IP addresses were identical. It's like having two people named John Smith, but one lives in the US, one lives in the UK. The country code, like the RD, keeps their mail separate. This lets providers host lots of VPN customers safely, even with overlapping addresses.
That's a really clever trick to keep everything separate behind the curtain. All right, let's talk security. Firewalls. The question identifies C, Access Control List, ACL, as the key thing preventing unauthorized access. What exactly is an ACL? How does it decide who gets in?
Okay, an ACL, an access control list. It's basically just a list of rules. You configure these rules on a firewall, sometimes on a router too, and these rules act like your security policy.
Like a bouncer's list.
Kinda, yeah. A very specific bouncer's list. Each rule specifies what kind of traffic is allowed or denied. It looks at things like the source IP address, the destination IP address, the port numbers being used like web traffic on port 80 or 443, and the protocol like TCP or UDP. So when a data packet arrives at the firewall checks it against the ACL rules, usually in order. The first rule that matches the packet's details determines its fate. Allowed through permit or blocked, deny.
And if nothing matches?
Usually there's a default rule at the very end, and often that default is deny. So unless you specifically allow something, it gets blocked. ACLs are fundamental. They're how admins control traffic flow and enforce security.
So a very detailed set of yes-no instructions for network traffic.
Got it.
Okay, nearly there. Penultimate question takes us back to routing protocols. Which one uses a link state database to build a map of the network? We touched on this. The answer is BOSPF. Why is this whole map building thing such a good approach for routing?
Right. OSPF and its link state database, it's a different philosophy from older protocols. With link state, like OSPF, each router doesn't just learn about routes from its immediate neighbors. Instead, every OSPF router learns about the status of all the connections, all the links in its area of the network. They exchange special messages called link state advertisements, LSAs. These LSAs basically say, here are my connections, here's who I'm connected to, and here's the cost or speed of those links.
Okay.
All this LSA information gets collected by each router, and each one uses it to build an identical, complete map the topology of the network area in its own linked state database.
Everyone gets the same map.
Exactly. And because every router has this complete map, it can independently run an algorithm, usually Dijkstra's algorithm, to calculate the absolute best, shortest path to any destination on that map. This generally leads to more accurate routing and, crucially, faster recovery if a link goes down, because everyone can recalculate the best paths from the map they already have.
Makes sense. Instead of just asking for directions step by step, everyone has the full map to find the best route themselves.
Mm-hmm.
Okay, final question. Back to BGP one last time. It identifies BAS path as a mandatory attribute used in route selection. What exactly is the AS path, and why is it so vital?
Okay, the AS path. It's fundamental to BGP. It's basically a list of all the autonomous systems, the ACEs, that a particular route advertisement has traveled through to get to you.
And an AS is like a big network provider?
Yeah, generally. A large network or group of networks under a single administration, like an ISP or a major company. So when your BGP router gets an update about how to reach some network, the AS path tells you the sequence of these big AS networks the traffic would have to cross.
Okay, why is that mandatory?
Two main critical reasons. First, loop prevention. This is huge. If a router receives a BGP update and it sees its own AS number already in the AS path list, exactly, it means that route somehow looped back around. The router knows this is bad and discards that route immediately, prevents traffic going in circles forever.
Smart. And the second reason?
Path selection and policy. The AS path is a primary factor BGP uses to decide the best route if it learns multiple ways to reach the same destination. Often, shorter AS paths are preferred, fewer networks to hop through. Plus, network admins can create policies to say, I prefer routes through this AS, or I absolutely want to avoid routes that go through that AS, maybe for cost or performance reasons. Because it's essential for loop prevention and core path selection, AS path is mandatory. Can't have BGP without it.
Right, okay. That makes sense why it's so crucial. Think about the principles we saw. Organization like IS levels, prioritization like QoS, clear identification like MPLS labels or RDs, rule-based control like ACLs. How might those same ideas, organization, priority, identity rules, be working quietly in other complex systems, maybe even in our everyday lives? What other hidden structures are keeping things running smoothly?
That's some interesting food for thought.
Definitely something to ponder. Well, that wraps up this deep dive. Until our next exploration.